in time. So please, Yacine, so we'll have the second lectures about CMB.
Okay. In fact, maybe, okay, I was going to join simultaneously with my video, but no one needs to see my face, I suppose. As long as you can hear me. Okay, so let's start the second lecture on the cosmological ionization history. And please tell me also if you don't hear me properly. Huh? So just as a recap, the goal, what goes into calculating CMB anisotropies is all of these interactions that are highlighted here. All gravitational interactions between photons, baryons, neutrinos, and cold dark matter. What the focus of this lecture is going to be is specifically on the baryons. You can see my screen when I do this?
Yes.
Very good. Okay, let me know if there's anything. Okay, I'm going to also change. Sorry, this is experimental. Okay, so we're going to study recombination. Why? As I mentioned yesterday, because free electrons, which are the little red dots here, is free electrons, scatter Thompson scatter photons up until when the universe was approximately 400,000 years old. And then photons scatter for one last time, and this is what we see as the CMB. So the goal of this lecture is to quantify, first of all, what it means by this scattering one last time, and secondly, to quantify how exactly did the universe go from ionized to neutral, as exactly as we can. Okay, so let me start by setting up some definitions. So the free electron fraction, denoted by XE, which depends on redshift, is the ratio of the number density of electrons to the number density of neutral hydrogen, which I denote by H0, plus ionized hydrogen, i.e. protons, NP. And the denominator, I will also denote NH for short. So NH is the total number density of neutral plus ionized hydrogen. And so, in other words, NE is just XE times NH. So one thing to keep in mind, the characteristic density in the of the mean density of hydrogen. So all of those are mean densities, by the way. I'm not going to keep writing all the mean densities. So this is of order 300, just to have an idea, atoms per cubic centimeter. And it scales as 1 over the scale factor cubed, i.e. 1 plus z cubed. So around recombination, we have about 300 atoms per cubic centimeter. The Thompson scattering cross-section, this is of order 6 times 65 times 25 centimeters squared. Okay, so given this mean density of hydrogen atoms, given the mean density of free electrons, one can compute the probability for a given photon. What is the probability that it will Thompson scatter between the time interval t to t plus dt? And this probability, I'm going to denote it by dp scat. This is just equal to the Thompson cross-section times the number of scatterers, the number density of scatterers, times dt. And here again, I'm using that speed of units in which the speed of light is 1. Okay. So let me highlight this. All of these notes will be available much more cleanly written, are already available on the website. Okay, so now we can compute more things. We can compute what is the average number of scatterings in a finite time interval. So this average number of scattering, I'm going to sum over, or rather integrate over, the probability of scattering in a infinitesimal time interval, i.e., which this probability, you can also think about the fraction of scatterings in an infinitesimal time integral. This is also, so if T0 here is taken to be today, this actually we denote as tau of T, comma T0, and this is the Thompson optical depth, just for a little bit of jargon. Okay, given this Thompson optical depth, we can compute the probability that a photon will no longer scatter ever after time t. So this probability of no scattering between t and t0 is exponential of minus the mean number of scattering, i.e. minus the optical depth. And you are asked to explicitly prove this in the homework. And so as a consequence, if I ask what is the probability of scattering for the last time in some time interval, so this I will denote by this G subscript T of T. You'll see why I'm using the subscript T. So this is going to be the probability of scattering in the interval T to T plus dt. And I want it to be for the last time. So I want to multiply this by the probability of no longer ever scattering between T and T0. And so this function here is called the Thompson visibility function, and it will appear again later on in tomorrow or the day after's lecture when we study the line of sight integral for CMB anisotropies. This is a probability distribution, so you are asked to check explicitly for yourselves that it integrates to 1. This function appears actually not quite this function, it's not quite this one that's going to appear, but rather it's the same function but defined in terms of conformal time. So this is just a matter of changing variables. So this G eta times D eta is equal to the probability of last scattering in conformal time interval D eta, and so it's just given by this expression. And given that dt is a times d eta, so this is just the scale factor times the function I wrote before. And if you want now to ask what is the probability of last Thompson scattering per redshift interval, so again, this is just going to be a change of variables. So here we're going to have dt over dz. And so this is gt of t times dt over d log 1 plus c times d log 1 plus z over dz. And why did I write it this way? Because this is just 1 over the Hubble rate. So all in all, we get that this visibility function in redshift space, i.e. the probability of last scattering in a redshift interval z to z plus dz, this is 1 over this just conversion factor from time to redshift interval times the number density of free electrons, Thomson cross-section, times the exponential of minus the Thomson optical depth between redshift z and redshift 0, which is today. All right, so this is the visibility function, i.e. the PDF of scattering for photons. Now, if you compute the free electron fraction very accurately, and I'm going to tell you how one goes about in computing this free electron fraction, what you find here, I'm plotting the visibility function normalized to its peak. What you find is that it peaks around redshift of approximately 1080, okay, which is approximately 1100, which is why we say that CMB photons come from redshift 1100. Really, a more accurate statement would be to say that CMB photons are most likely to have scattered for the last time around redshift of 1100. And notice that this visibility function has some width, some finite width of order a couple hundred in redshift. So really, CMB photons come from a last scattering thick surface. Okay, so now our goal is going to be to understand. So this again is proportional to NE sigma Thomson times this exponential of minus integral dt and e sigma Thomson over between time t and time t0. So our goal is to compute this free electron fraction, hence the free electron density. Let's start with a very, very, very ultra naive. Emphasize this is really super naive. So the temperature of CMB photons today is 2.73 Kelvin. We know that this temperature was hotter in the early universe. It scales as 1 over the expansion factor, which is 1 plus z. Now, useful thing to remember is, at least I find it useful in terms of these kind of calculations, is to remember that 1 electron volt corresponds to 10 to the 4 Kelvin, okay, in terms of conversions. So the temperature of the universe of photons around redshift 1000 is approximately 0.2 electron volts. In contrast, the ionization energy of hydrogen is 13.6 electron volts. So a very, very ultra naive estimate. If I ask, when is the temperature of the universe of photons equal to the ionization energy? This would imply Z approximately 60,000. This is much, much, much higher than the actual recombination redshift. So this is very, very naive. A slightly less naive estimate, but still very naive, would be accounting for the fact that there is a huge number of photons per hydrogen atom, about 10 to the 9. And again, in the homework, you're asked to compute this explicitly. Why is it 10 to the 9? Take a black body spectrum for the CMB, take number density of atoms of 300 per cubic centimeter at redshift 1000, and figure it out as 10 to the 9. So at any given redshift, if I plot, for example, dn photons per logarithmic interval in photon energy, here as a function of photon energy, I have a black body spectrum. So the peak is around T. Okay, you can figure out exactly where the peak is. But really, the photons that do matter for ionizing hydrogen are the photons whose energy is larger than 13.6 electron volts. So a less naive estimate would be to say that hydrogen becomes neutral when the number of photons whose energy is greater than the ionization energy of hydrogen is comparable to the number of hydrogen atoms. And if you do this estimate, which again, you're asked to do this in the homework, you will find a recombination redshift, which is closer to the correct answer, which is around 2000. And that's still much higher than the correct answer. Moving on in our quest to get less and less naive estimates, we can now try to, because those previous estimates just give us some characteristic, one single number. Okay, so now if I really want to have a time evolution of the free electron fraction, I can make a still naive estimate, which is called the Saha equilibrium estimate, which is the assumption of equilibrium. So specifically, what are the assumptions? So first, and this is the equation that is Saha equilibrium. Okay, so this is this equilibrium. But let me tell you what goes into these assumptions. And again, you are asked in the homework to put these together and derive this yourself. So first, the reaction, the recombination and photoionization reactions are assumed to be in equilibrium. The second assumption is that the temperature of baryons, which I will also sometimes you'll see it equal to temperature, denoted as the temperature of matter. Okay. This, by the way, is equal to the temperature of electrons, which is equal to the temperature of protons, neutral hydrogen, and helium. Okay. So the second assumption is that this is equal to the temperature of the photons, that matter and radiation are in thermal equilibrium with one another. The third equilibrium assumption is that photons, i.e. the CMB, are a perfect black body at all energies. So what we measure observationally is the cosmic microwave background around the peak of the black body spectrum. Okay, we don't measure it in particular here very far in the tail where the ionizing photons live. Okay, this is really, really far. So this, again, remember, is 0.2 electron volts. So this is a factor of what? 5 times 13, 50 60 higher than the peak. So we don't measure directly the black body spectrum there. And so this assumption implies that the photons have a zero chemical potential. Okay. In fact, this assumption is violated, very strongly violated. So if you put these assumptions together, and from the first equation, equilibrium implies that the chemical potentials of electron plus the chemical potential of protons equal to the chemical potential of hydrogen, neutral hydrogen plus that of photons. From the last equation, I'm going to set this one to 0. And so this equality, you're asked to show this for yourselves, implies this equilibrium free electron fraction. Okay, so this again is proportional to the ionization energy of hydrogen, exponential minus 13.6 eV over temperature, inversely proportional to the number of hydrogen atoms. Okay, so this is how this Saha equilibrium equation, if you plug it in, looks like as a function of redshift. And the solid line would be if you have a correct calculation. And again, you see that now this equation, which is less naive, much less naive than our first two estimates, is still vastly wrong in terms of getting the correct free electron fraction. So what are now the actual dynamics involved in computing the free electron fraction? So all of these assumptions that were in the Saha equilibrium equation break down at some point or other. So let's start with this assumption of equilibrium of this reaction, which is the most important assumption. So we want to, rather than assuming equilibrium, we want to figure out what is the rate of these equations. So first of all, what is the rate of the equation moving forwards? Electrons and protons recombining or combining to form neutral hydrogen and atoms. This is controlled by a coefficient, which is called the recombination coefficient, which depends on temperature. This has dimensions of, well, has units, I'm going to units of centimeter cube per second, so dimensions of volume per unit time, and is defined in such a way that the number density of the change of the number density of free electrons through this process, so this is a negative value because this process is destroying free electrons, times NE times NP. So you see that with these units, indeed, this gives you the left-hand side here, gives you the correct units. So this is the definition of this recombination coefficient. Now let's look at the reaction moving the other way. How do neutral hydrogen atoms get photoionized by photons? So this is controlled by some other coefficient, this beta photoionization. And so this beta photoionization has units of inverse seconds. It's a rate. And it is defined such that the rate of change of the abundance of free electrons due to photoionizations is this coefficient, beta photo, which depends on temperature. We'll see exactly how it depends on temperature, times the number of neutral hydrogen atoms. So if I write this now in terms of my XE, free electron fraction, and if I assume, so here we're going to focus, I should have said this, on hydrogen recombination. I'm not going to talk about helium recombination. It's very interesting physics, but it doesn't matter quite as much for CMB, though it does matter to some level. You can look at papers by Chris Hirata and Eric Schweitzer, for example, where they work out helium recombination. So if I assume that helium has fully recombined, then Ne is equal to NP. There are as many free electrons as there are free protons. And this one is equal to beta photoionization of temperature times the total number density of hydrogen times 1 minus the ionized fraction. Okay, so this 1 minus XE is equal to the neutral fraction of hydrogen. All right, so if we now put everything together, the recombination equation here, and then the photonization equation here. We divide these two equations by NH, so I can get a rate of change of the free electron fraction. What you get is an equation that governs the evolution of the free electron fraction, which is what we were looking for. And it looks like this. And I need an xe squared plus beta photoionization, which depends on temperature, times 1 minus xe. So this is, let me move this here. So this is a very generic equation to govern the rate of change of the free electron fraction. I haven't yet told you anything about what goes on into calculating this alpha and this beta. So let's start by asking how these two coefficients are related. And what I'm going to walk you through now is called a detailed balance argument. It's extremely common and extremely useful in physics. So first, let's consider the left-hand side here. So the free electron fraction here, we're interested only in the average free electron fraction, and we will see why tomorrow. We don't care about the spatial perturbations. Most background quantities in the time of interest evolve on a time scale, which is the Hubble time scale. Okay, they don't change super fast compared to the Hubble time scale. That means what? That means that dxe dt is of order xe times the Hubble rate. Okay, so if I compare now this term on the left to that term on the right, the first term on the right, we'll see that if NH times alpha recombination times xe, if it's, so I divide everything by xe, if it's much greater than the Hubble rate, so this has units of inverse seconds, and also this has units of inverse seconds. So we reach, if that is satisfied, we reach an equilibrium. What is this equilibrium? Is obtained by setting the right-hand side of this equation to 0. So I can neglect this left-hand side relative to that first term here. So then if I set this to 0, I will get the equilibrium being this photoionization rate divided by NH times the recombination coefficients. Both of them depend on temperature. Now, if I assume the other two conditions of the Saha equilibrium, if I assume, moreover, that the temperature, I haven't specified what temperature, if I assume that it's the same for matter and radiation, and if I assume that photons are a perfect blackbody spectrum everywhere, then this equilibrium should be exactly what I obtain from the Saha equation. And this implies that this photoionization coefficient is just equal to, there's a relationship between photoionization and recombination, which is given by this equation here. Again, this is called a detailed balance argument. So where does this relationship come from in a fundamental level? It comes from the fact that these two processes here, this one and this one, are governed by exactly the same microphysical cross sections. They're governed by exactly the same microphysical matrix elements. Okay, so these are just the time reversals of one another. I'm sorry for the noise. Okay, so these are just the microphysical time reverse reactions, and as a consequence, their rates must be related. And the fact that they depend on temperature is just because we're averaging over thermal distributions of either electrons and protons in this case, or of neutral hydrogen and photons. Okay. All right, so this is how we relate these two coefficients. Now, if you take the simplest possible estimates of these recombination coefficient, which then gives you from this equation the photonization rates, and you compare this coefficient to this rate, sorry, the recombination rate to the Hubble rate, you find this evolution. So you find that in the early universe, it is larger than the Hubble rate, but around redshift 1000, it will fall under the Hubble rate. And so this tells you that this equilibrium assumption cannot be satisfied. And in fact, here I've taken a really, really naive estimate of alpha recombination, but in fact, this is even further suppressed, as we will see now, when you do a more detailed calculation. So in fact, this would fall below unity even earlier than redshift 1000. The point I'm making here is that the evolution of the free electron abundance in the universe, the ionization history in the universe, does not occur at all in thermal equilibrium. And so instead, we need to compute the dynamics of the recombination of hydrogen. And so to do so, we first need to understand, to remind ourselves, what is the internal structure of the energy states, of the bound states of hydrogen. So hopefully you remember this from quantum mechanics, that hydrogen has energy bound states, which are described by a principal quantum number, n. This principal quantum number tells me that the energy of the bound state, it quantizes the energy of the bound states, and the energy is minus 13.6 eV over n squared. It also has a quantum number L, which goes between 0 and n minus 1, which is why these lines stop here at L equals n minus 1. And there's an additional, so this is the angular quantum number, and there's an additional m number, which I'm not showing here. Now, the energy states here, just to be clear, between the n equal 2, so n equal 2 will have a special role. So between n equal 2 and the continuum, i.e. ionized hydrogen, here we have 3.4 electron volts, and here we have 10.2 electron volts. Now, one point which is important to keep in mind is that at any given time, the number density of hydrogen in any of the excited states NL, where n strictly greater than 1, over the number density of hydrogen in its ground state, 1, 0, it's extremely, extremely small compared to 1. As a very naive estimate, you can estimate it to be of order the degeneracy factor of the state L times exponential minus En over minus E1 over T. And this is at least, this here is at least 10.2 EV. And again, remember that the temperature is 0.2 EV. So you see that this is suppressed by e to the minus 50. Okay, so this abundance is extremely small at all times. So basically, hydrogen is either photoionized, so in the form of electron plus proton, or mostly in ground state. Again, I'm sorry, this is not super pretty here, but I promise my saved notes are much nicer. You just have to follow my voice. Okay, so this is the first thing I wanted to discuss. Let's get a fresh page now. So another thing I want to discuss, because of this very small abundance of hydrogen in any of the excited states, all of these transitions, so let me first mention something here, is that the radiative transitions between different bound states must obey some selection rules, which is that they change angular momentum by plus or minus 1 for electric dipole, so-called allowed transitions. This is because the photon has angular momentum 1, has spin 1. So these are, for example, how these transitions look, you can have transitions between L equals 0 and L equals 1, between L equals 1 and L equals 2. It doesn't have to be just 1 and above. It can be 2 n's above, for example, here, like so. And you also have transitions from bound states to the continuum, okay? Now, all of these transitions here between excited states among themselves or between excited states in the continuum are optically thin. What does that mean? That means that the optical depth, which is the probability of a photon to be absorbed, for a given photon, what is the probability that's going to be absorbed in any one of these transitions, it is always much less than unity. And these transitions, by the way, all go both ways, okay? So these transitions, because they're optically thin, they do not significantly add or subtract photons to the CMB. So the CMB remains a black-body spectrum at the corresponding frequencies. However, this transition here is called the Lyman alpha transition. And this transition is so-called optically thick. And in fact, all of the transitions to the ground state, so there are other ones, there's the Lyman beta, and there's the Lyman continuum transition. All of those transitions are optically thick because at any given time, even if hydrogen is almost mostly ionized, they have such a high rate that even a small fraction of ground state hydrogen is enough to give a significant probability of photons to be absorbed in these transitions. Okay. So now to the question of how does neutral hydrogen form, starting from electrons and protons, free electrons and protons. The first naive pathway would be to say that you could have direct recombinations to the ground state. Now, every time such a direct recombination happens, it results in the emission of a photon with energy above 13.6 eV. It's not exactly 13.6 eV because this electron and proton have some thermal energy. And so the photon gets not only the binding energy, but also a little bit of thermal energy. Now, if you ask what is the time scale for this photon to be reabsorbed by another hydrogen atom in the ground state. So this is going to be 1 over the number density of hydrogen in the ground state times the photoionization cross-section. So this is just 1 over the rate of photoionizations. And this, if you plug in numbers, you will find that this is much, much less than a Hubble time, as long as 1 minus xe is greater than something like 10 to the minus 9. As soon as the free electron fraction, the neutral fraction is greater than 1 part in a billion, then photons resulting from direct recombination to the ground state get immediately reabsorbed by another hydrogen atom. So the bottom line here is that these direct recombinations are basically, they don't count. Every time they happen, they get immediately canceled out. This photon gets reabsorbed, and so you have one atom that forms, but another one gets destroyed. So instead, what we want to account for are only recombinations to the excited states of hydrogen. Right? So this is in terms of the jargon used in the interstellar medium community. This is called a case B recombination. In case you read this somewhere, you know what it means. So recombinations to excited states only. So each one of those recombinations is characterized by some recombination coefficient. Again, the same one as before. This has units of inverse cubic centimeter inverse time. And this depends on two temperatures. Now, to be a little bit more accurate than before, it depends on the baryon or matter temperature, because it depends on how fast these electrons and protons are moving when they recombine. And it also depends on the photon temperature, because these transitions, all of these transitions can be stimulated by photons. Okay, so this is one first piece of microphysics that one needs to compute to study recombination. All right, next. Suppose we now have an atom that made it to one of these excited states. So it has recombined to one of these excited states. So what is its future? What is its fate? Either it will, say, be excited by absorbing a CMB photon to another state, and maybe from there it can decay here to the n equal 2. Or it can do this, maybe I'll do this more indirectly. Maybe it can go to some other excited state, and then here, and then eventually it can end at n equal 2. So either it will end eventually after some transitions at n equal 2, or it will first, say, get excited, again, respecting the selection rules, to some other state, and then eventually it might get photoionized. Okay, but there are two ends to this atom that forms in an excited state. Either eventually it gets to n equal 2, or eventually it gets to it gets photoionized again. In which case, if it gets photoionized again, well, we don't really care. We only care to know for atoms that actually do make it to at least to n equal 2. So let's call this probability of making it to n equal 2, p from NL to 2. This depends on the temperature of CMB photons, because all of these transitions are mediated by blackbody photons. And so from this, we can construct an effective recombination coefficient to n equal 2. This is something that myself and Chris Hirata described in 2010, if you want to read this paper, or you can read my thesis. You'll be the third person to read it. So this is the sum n greater than 2 L of this recombination coefficients, which depends on the photon and baryon temperature, times the probability that the atom eventually ends in n equal 2. Okay, so now we want to use this rather than this is what goes into computing this recombination coefficient, and there's still some more to be described. And then corresponding to this, there's also a effective photoionization rate, which only depends on the CMB temperature. Okay, next, so this is how electrons and protons end up to n equal 2, or get photoionized again. Once they are in n equal 2, what happens to them? Well, either if they ended up in, say, the so-called 2p state, so this p means L equals 1 in terms of atomic spectral nomenclature, well, they can decay to the ground state by emitting a Lyman alpha photon. This is this Lyman alpha transition at an energy, again, which is 10.2 electron volts. All right, this is a very strong transition. It has a spontaneous rate, an Einstein A coefficient, which is 6 times 10 to the 8 per second. So naively, you would think that, well, if the atom ended up in n equals in the 2s state, which is L equals 0, well, there's no pathway from this state, so we really have to focus on the 2p to ground state transition, because this is the only dipole allowed transition, and we'll see that it's not the case. So Why is it not the case? Because these photons here that get radiated at an energy of 10.2 electron volts get almost always reabsorbed by some other neutral hydrogen atom. Okay, just like the Lyman continuum photons, just as the photon 13.6 eV and above photons got almost always reabsorbed, those photons also get almost always reabsorbed. Except here we have, well, in both cases, but here what we have to account for is the fact that this is a resonant transition. And if the photon, before getting reabsorbed, has redshifted sufficiently out of the resonance, then they may no longer be reabsorbed. They may escape reabsorption. So there is some probability of escape, which is going to be proportional to the expansion rate, because the faster the expansion rate, the faster photons redshift, and the faster they will no longer be in resonance with the 10.2 electron volt transition. This escape rate is going to be inversely proportional to the number density of neutral hydrogen atoms, because this is the more you have absorbers, the less photons can escape, and inversely proportional to the rate of the transition itself. And if you really want to make this a little bit more correct, there are some packed factors of pi, and you want this to make this dimensionless. This has dimension, this is a rate, this one is a rate, this is a density, so I need to multiply by a length cubed, and the length cubed turns out to be the Lyman alpha frequency, which is 1016 Armstrong, if I'm not messing this up. And this, if you plug in numbers, typical numbers around redshift 1000, you get an escape probability of about 10 to the minus 8 or so. So then the net rate in this transition is going to be the escape probability times this spontaneous coefficient. And this will be between 1 and 10 per second. So this is much, much, much smaller than the naive 6 times 10 to the 8 per second. So in fact, this transition appears to be very strong, but really you have a lot of reabsorptions. Most of the photons emitted in these transitions are reabsorbed, and only a very small fraction of them make it and provoke a real effective transition to the ground state. And so this transition is so weak that in fact we must account for transitions from the 2s state, which is again the L equals 0 state. So I told you that there are no electric dipole transitions, single photon electron dipole transitions allowed between states of the same angular momentum. However, you can get a 2 photon transition from the 2s state to the ground state. So this is the second order in terms of a perturbation theory in quantum mechanics. You can obtain this transition at second order. So this is this 2 photon transition. Sometimes it's called forbidden in the sense that it's second order. So it's a much suppressed rate. And it has a rate of 2 photons transition, which is 8.22 per second. So this relative to the 10 to the 8 per second is very small, but this is actually comparable to the 1 to 10 per second for Lyman alpha transition. So in fact, this 2 photon transition, and this was first figured out simultaneously by Zeldovich, Kurt, and Sunyaev, and also by Peebles, both in 1968. And they both recognized the importance of this forbidden transition to the recombination process. So moving on, putting things together. So if I start somewhere in n equal 2, either I will get, say, excited to some other state, and then excited again, and then maybe some decay, and then photoionized. Or I will transition to the ground state, either through Lyman alpha or through 2-photon emission. So again, if I asked, starting from n equal 2, the end states, I have either I can get photoionized, and we already talked about the effective photoionization rate from n equal 2, which accounts for these possible indirect pathways. It can be direct photoionizations, but it can also be indirect photoionizations. Or can decay to the ground state through either Lyman alpha or 2-photon transition. So the net rate for a decay to the ground state, if to simplify, I assume that the n equal 2 angular momentum substates are in equilibrium, which is not quite correct for detailed calculation, but as a simplifications, we can do this here. The average rate is going to be obtained by weighting these two transition rates by the fraction of hydrogen in the L equals 1 state, which has 3 momentum M substates, and 1/4 for the L equals 0 state. So then we can find the probability for a atom which is initially in n equal 2 to reach the ground state rather than being photoionized. So this is the ratio of this net decay rate to the ground state to the sum, the inverse lifetime of the n equal 2 state. All right, so let's put everything together now. Remember that before we were talking about some recombination coefficient, but I didn't tell you exactly how it can be calculated. So now I've highlighted the ingredients to compute it. We need to compute first the effective recombination coefficient to n equal 2, because direct recombinations to the ground state don't really count. They effectively cancel out, times the probability or the effective probability that an atom in n equal 2 reaches the ground state. And that tells me the effective rate of recombining, of making ground state hydrogen. Just like before, the photoionization rate can be related to the recombination rate at the appropriate, at the same temperature, because this depends on photon temperature, through this detailed balance argument. And so again, now putting it together, we are back to this equation which I wrote initially. But now I told you what goes into computing these coefficients alpha and beta. Some additional complications which I did not mention in this description. First of all, I only talked about Lyman alpha, but you also want to account for higher order transitions to the ground state. They also contribute to transitions to making ground state hydrogen. And secondly, to compute this net probability of going from n equal 2 to the ground state, or for example, to compute the Lyman alpha escape rate, really what you want to do is compute to solve the Boltzmann equation for Lyman alpha photons, or for photons around the Lyman alpha frequency. And the Boltzmann equation in this context has a different name. It's called the radiative transfer equation, but it's nothing but a Boltzmann equation. And this is what modern recombination codes, such as HiREC and Cosmorec, compute. They solve the radiative transfer equation so they solve for the non-equilibrium of the radiation field, from which they can estimate the decay rate to the ground state. And then putting it in these kind of equations, you can get the differential equation for the evolution of the free electron fraction. Okay, another aspect that goes into Saha equilibrium, or the equilibrium assumption in general, is that the matter temperature is equal to the baryon temperature. So given that I'm running a little bit late on time, I'm gonna switch to my pre-written notes. So we're gonna go straight here. All right, so first and foremost, I saw that Fabian had this in one of his slides. I don't know if he talked about it in detail, but electrons, protons, hydrogen, neutron hydrogen, and helium, they're all in thermal equilibrium with one another. Okay, and this is because electrons and protons have charges, so they scatter with one another through Coulomb scattering, and then charges can scatter off of neutral atoms through a charged induced dipole scattering, and those have rates which are very, very large compared to the Hubble rate, and as a consequence, they are all in thermal equilibrium. So they all have the same temperature. So when I talk about the baryon temperature, I mean the same temperature for electrons, protons, helium, etc., etc. All right. Now, if I consider the effect of the expansion of the universe on the temperature of photons, the temperature of photons is nothing but the characteristic energy of photons with just some numerical prefactor in front of it, a constant prefactor. And photons have an energy which is equal to their momentum. And as we said yesterday, this decays as 1 over the expansion, the scale factor of the universe. On the other hand, baryons, also their temperature is the characteristic energy of baryons. And the characteristic energy for a non-relativistic species is just p squared over 2m, where m is the mass of the species of interest, whether it is protons or electrons. And this would decay as 1 over a squared in an expanding universe if nothing was otherwise heating up the baryon. So this is called, if the baryons were cooling down adiabatically, their temperature would go as 1 over a squared. And so their temperature, of course, would no longer be equal to the CMB temperature. But in reality, Thompson scattering, again, Thompson scattering is really a crucial a piece of physics in CMB, is pushing the baryon temperature towards the photon temperature. It's trying to maintain the electrons and the photons in equilibrium with one another. But it doesn't succeed at all times. So how does this work? So let's consider a Thompson scattering event. Here's my initial state. I have here, to simplify, an electron which starts at rest. So I'm going to the rest frame of the electron. Some photon which has a momentum p gamma, which is p gamma times some direction of propagation. And now in the final state, the photon is scattered in some other direction. It has p gamma prime momentum. And then to conserve momentum and energy, the electron will also acquire some recoil velocity. So now if I write down the conservation of energy here and the conservation of momentum here, and you put them together, so if this is going a bit fast, I encourage you to do this yourself, but basically you put this first equation, you subtract p gamma minus p gamma prime from this first equation, and then I substitute this from the momentum equation. And what I find is that the change in momentum, in photon momentum, is of order the momentum squared of the photons over me. Okay, so if I divide everything by p gamma, we find that the fractional change in photon momentum is of order the momentum or the energy of the photon over the electron mass, which is of order the temperature of photons over the electron mass. Now, the temperature, as I said before, is 0.2 electron volts, around redshift 1000, and the electron mass is 0.5 mega electron volts. So this ratio is about 10 to minus 6, is less than 10 minus 6 at the epochs of interest. So the bottom line here is that at the epochs of interest, Thompson scattering does not change photon energy. You can assume that photons remain with the same energy and that they only change orientation. They only change direction of propagation. And this does matter very much, this change of direction of propagation, as we will see tomorrow when we study the Boltzmann equation for photons. So now back to computing the energy given to the electron. So again, the final energy of the electron is given by this using the momentum conservation equation. And if I use the fact that p gamma prime and p gamma have the same magnitude but different direction, hence the n prime versus n here, I can pull out the p gamma out of this equation here, and I'm left with this, where this n dot n prime is the cosine of the angle between the initial and final directions. Now, one more ingredient is to know that the angular distribution of Thompson scattering is given by this equation here. It has a monopolar term and a quadrupolar term. And in particular, the average over final directions of scattering of this term here. So this averages to 0. So if I take the average of this final energy here over final directions, I get P gamma squared over ME. If I then average over this further over the energy of photons, I'm going to get that the final energy of the electron after scattering is of order temperature of photons squared over ME. So then I can ask, what is the rate of heating of electrons per electron per unit time? And this is going to be of order this T gamma squared over ME here, times the rate of scattering with photons, which is just sigma, the Thompson cross-section, times the number density of photons. And then if I remember that sigma, that number density of photons times their temperature is basically just up to some numerical prefactor, the energy density of photons, I can simplify this to this equation here. Now, if I ask per unit volume, what is the heating rate per unit volume? I'm going to get the number density, this gives me the per unit volume of electrons, times the rate of change of the electron energy per unit time. And then we get this equation, number density of free electrons. Again, this is proportional to XE, which we just talked about. Thompson cross-section, rho gamma over mass of the electrons times T gamma. Okay, I'm going to be like just 5 minutes late. Is that okay? I don't know if I don't see people here. So Raul or Paolo, please.
Yeah, I think it's okay, Yacine. Yeah.
Okay, all right. So electrons now are very generous, and they're going to share all this heat with protons, the hydrogen atom, helium atoms. Okay, so in fact, every time they get some energy per unit time per unit volume to the electrons, this is shared with all the baryons. Okay. Now, what is the baryon thermal energy density? It's 3/2 of number density of baryons times the temperature. So what goes into this number density of baryons? You have the number density of protons, neutral hydrogen, electrons, helium, in all its form, ionized, singly ionized, and neutral helium. Now, this whole thing for helium here is just number density of hydrogen times the helium mass fraction. This Ne is just free electron fraction times NH, and this is just NH. So if I divide everything by NH, this is where I get this equation here. And so now if I plug back what we found just before, which is the rate of change of the energy density of baryons, this is going to be equal to NH times 1 plus Xe plus F helium times the rate of change of T baryon. So I can write this into an equation for T baryon. And here what I've done is I've added the correct factors by including stimulated scatterings. And this term here accounts for the fact that you cannot heat up the baryons above the CMB temperature. There is also a recoil term that has to be accounted for. But so basically this is described up to the numerical prefactors, all of the physics that goes into one of the important equations that you solve, which is the evolution of the temperature of the baryons. And by the way, if for those who followed the edges results and for 21 centimeter, this is also a very important equation for 21 centimeter, because baryons remain coupled to photons down to Z of about 200. And exactly when they decouple will then result in, we'll then be able to compute the temperature of baryons, hence the 21 centimeter temperature at much later redshifts. So I'll just take this last 3 minutes to mention reionization. So reionization is part of the ionization history of the universe. It's not recombination. It's a completely different physical origin. So the origin here is that around redshift of 20 or 30, the first nonlinear structures form and the first stars in the universe form and turn on. Then you have the first proto-galaxies, supermassive black holes, quasars. All of those generate a lot of radiation, ultraviolet, X-ray radiation. This radiation is going to go and heat up the universe, and also is going to contribute ionizing photons, which can ionize the gas beyond the calculation that I described for recombination. Now, as we will see, again, probably in 2 days, CMB anisotropies depend on reionization mostly through one single parameter, which is the optical depth to reionization. Precisely what this means, this is the optical depth that is additional to the optical depth from just regular recombination. So there is some optical depth, of course, that goes to order unity at the last scattering surface, okay, from the regular recombination history. So this is what I call this NE, no reionization. Now, with reionization, we get an additional delta NE here, which contributes an additional optical depth. Okay, so this is what we call the tau reionization. And this is measured to be of order 5% or so. You can look up the detailed numbers in the last Planck paper. So, for example, if you assume that reionization happened instantaneously at some redshift Z reionization, so the picture here is that we start with a universe which is fully ionized. Around redshift 1000, we have recombination. Most CMB photons scattered for the last time from this redshift. But then around some redshift Z reionization, which could be between 5 and 10, the universe gets, and here we're going to assume, fully reionized. And so in this simple case, the optical depth to reionization is just the integral between 0 and the reionization of the Thomson optical depth. Okay. And one of the things you're asked to do in the homework is to figure out what is the relationship between tau reionization and Z reionization if you have a matter-dominated universe or energy-dominated universe, and if you can estimate, given the measurement of Planck, what redshifts of reionization this corresponds to. All right, so this is the end for this lecture. And tomorrow, we will talk about this Boltzmann equation for photons. We will go in great detail solving this Boltzmann equation. Well, not solving, writing down the collision operator, the Thomson collision operator, and talking about the left-hand side of this equation. Okay, so I will stop my sharing now, and I will take questions.
Thank you. So let's have
Are there, I think are there any questions?
a few questions.
Yeah, I think Paulo is kind of freezing.
Okay.
And we can. So, there were many questions, but some of them were already answered by some other participants. So I wonder who wants. So maybe if you can raise your hand, or you just start talking, asking questions. It's okay at this point.
Okay.
Well, there is, for instance, there is a question about can you recommend some textbook? So I think this is a very nice general question.
Okay, for specifically recombination, I sent in the link in the notes for the introduction to my PhD thesis. I think that would be a good pedagogical reference. But as a textbook, I guess, you know, the Dollison and Schmidt textbook would be a good textbook. I haven't read this edition yet. Let's see what are the questions. Did you see any?
Yeah, so for instance, there is a question just added now. Why exactly did we assume that d mu in dt is equal to 0? The time derivative of mu is equal to 0 for photons.
So I think I only assumed that mu was equal to 0 when I was talking about the Saha equilibrium, right? When I was talking about this very naive estimate. But otherwise, at the frequencies of interest, for example, Lyman alpha frequency and Lyman continuum frequency, photons do have a very large chemical potential. They're not at all a black body spectrum. So that's part of the details of this calculation, is that you have to evolve the photon spectrum. Let me censor this.
Yeah, so then there is another question. Can you please tell us how we get the redshift spectrum in the first slides?
The redshift spectrum. I don't know what the redshift spectrum is.
Maybe Chaima, can you be more precise what you mean by this question? Or you just speak up?
Yeah, I don't know what the redshift spectrum would be. I can answer the question of why we talk about baryons. This is just jargon, cosmologist jargon. We should also say fermions, yes. But cosmologists use baryons to mean every particle that is normal matter. So indeed, it's not just baryons. Maybe I should have said this in the beginning. Let's see. So Rich, yeah. Is there any other question that you see, Paolo? That
well, some of them are already, there was a discussion.
I have a question.
Yeah, please go ahead.
Yes.
Maybe you can introduce yourself first of all.
I would like to know, apart from the importance of the ionization to the semi-B anisotropies, there is another influence of this process for the low redshift universe.
Oh, this is the question, whether there's an influence for the low redshift universe?
Yes. Apart from the influence to the CMB, which is the importance, which is the main effect, the other effects of the ionization time epoch to the present day universe.
So if you're asking like the ionization fraction around redshift 1000, then this really only matters to the CMB. However, actually, no, let me correct this. The ionization history, because it governs Thompson scattering, and thus it governs the coupling, as we will see tomorrow, between photons and baryons. This means that baryons are tightly coupled to photons, basically up until redshift 1000. They undergo acoustic oscillations. And then after redshift 1000, baryons are no longer supported by the pressure of photons, and they become effectively cold, just like cold dark matter. So they join in with cold dark matter, although they have some delay. And the acoustic oscillations also get imprinted, which were initially only in the baryons, get imprinted not only in the baryons, but also in the cold dark matter, because together they fall in the same potential wells. They interact through mutual gravitational interaction. So you probably have heard of the baryon acoustic oscillation in large-scale structure. So this is something that is not the CMB, okay, large-scale structure, the distribution of galaxies on large scales, which Fabian is talking about in his lectures. I don't know if he's going to talk about the BAO, baryon acoustic oscillation scale. But so the free electron fraction has an impact not only on the CMB, but also on this feature in the large-scale distribution of matter that one can actually measure. Now, beyond CMB and large-scale structure, the evolution of the free electron fraction at lower redshift, for example, through reionization, well, this would also come into the calculation of 21 centimeter, whether it is the sky averaged 21 centimeter spectrum or the fluctuations of 21 centimeter radiation, which have not yet been measured for sure, but that's something that could be, the future of cosmology, is to go and measure 21 centimeter radiation across cosmic times.
Thank you, Yacine.
Okay, we can take one last question. And so Gustavo Salinas is asking, are the photons resulting from the forbidden transitions enough in number to distort the CMB, or the large ratio and gamma over NH just makes their contribution negligible?
So they are, they do distort the CMB because they are, so the sum of the energies of these two photons. So I suppose you're talking about the two photon transition from n equal 2, L equals 0. So the sum of the energies is 10.2 electron volts. That is way, way in the tail of the CMB, the high energy tail of the CMB. So even though they're rare, even if you just have one transition more or less per hydrogen atom in the universe, they add up to a very small contribution of photons. So they do significantly distort the CMB, but this hasn't been measured directly yet, because these frequencies today fall in the far infrared background, where there are lots of other contaminants.
Okay, I see that somebody already downloaded your PhD thesis. So there is the link here on the thing.
Good. Yeah, I put it in the resources.
That's good. Okay, so we can maybe come back to the questions tomorrow. Let's thank Yacine, and we can conclude here. Thank you.
Right. You're welcome. See you
Thanks.
tomorrow.
Bye-bye, bye-bye.
Bye, thank you.